Hi folks, it's me again, I'm Funman. So today in this episode, we'll be speaking about the mechanisms for the destructions of the ozone layer, the O3 here. We look at certain reagents that could support in decomposing the O3 here, and we noticed that from the last part, we spoke about the halogen sources gases, and these are actually very stable compounds that contains like CFCs, highly compressed into liquid, very inert, but what happens is in the presence of UV light or sunlight here, right, or irradiations with enough energy here, they could be converted into the very reactive, the halogen gases, and this where these compounds or species will react with the ozone layer and form some other compounds. So remember, this part on the left here, they aren't the reactive substances, okay? But under a chemical conversions, when you have this catalyst, then you get these reactive gases, and then they will react with the O3 here, okay? So just want to sound that in the stratosphere, right, these halogen source gases chemically convert at a different rate. Some of them are more stable than the other. We notice that how the presence of more bromine atoms, right, will help to deplete the ozone layer faster than others because of the stability of the radical. We also talk about if you have a fewer hydrogen here, when you have more fluorine, right, then you have a higher possibility of forming more stable radicals. So in the next part here, we go through a few mechanisms on how the ozone is being destroyed. So in the cycle 1 here, you notice that you have got the very simplistic overview about one ozone molecule, right, O3, reacts with one oxygen atom to form two O2 molecules here, right? So this is a radical, right? This is a molecule, but they react, right, to form two oxygen molecules here. You notice? So this is still not so bad because you form O2, which we still require for respiration, so it's not that worst. But what happens is that, right, in the process, your chlorine atom here reacts with the oxygen to form a ClO here. So this becomes a self-catalytic cycle where you have a reactive Cl dot species to react and form ClO dot, and itself catalyze the formation of more Cl. You see this cycle here? So overall, what happens is you are converting O3 into O2, more O2 here. Got it? So this is what the mechanism states. Step 1 and step 2 here. You have the chlorine oxygen radical reacting with the O to form the chlorine radical and oxygen gas. Okay, fine. And then this chlorine radical reacts with more ozone to form a ClO dot and O2. So the overall reaction is a decomposition of the ozone into oxygen molecule. So now for this to occur, it's important to have the ultraviolet ray, which means that the ozone destructions, right, might occur much less if you do not have daylight here. Now, one question to think about is, what if it takes place maybe right now in between like the sunset here, right? So if you have enough ultraviolet rays, right, you start the process of forming this reactive chlorine atom radical, and then you self-propagate, remember, right? Because you have already generated the catalyst called the Cl radical and the ClO radical. And remember, catalyst will never be used up. It's regenerated, it has a high turnover frequency, and once you cause the catalyst to be formed here, it will just recycle itself and form. But of course, remember there's always a termination step where you have two radicals joined together to form a stable molecule, and this is where the reaction stops because you do not have enough radicals to continue the destruction of the ozone. So, the question is, where do the oxygen molecules come from in the stratosphere? Okay, now let's proceed to the second part of the mechanism for cycle 2 here. So let's start with cycle 2 on top here. Let's focus a bit more. So when you have the two molecules of the ClO dot, right, they can do a combination reaction, addition to form a dimer. Okay, so this dimerizations. But the thing is, when you form an OO single bond, it's highly unstable. It's like a peroxide bond. So what happens is the sunlight there will also split this intermediate into the chlorine radical and the ClO2 radical. Okay, now you might think that why it doesn't cut back the OO single bond. Yes, it can, but I'm saying that in this polar cycle 2, there is an alternative method to cleave the bond by the homolytic cleavage. So if it cuts here, then you have the chlorine radical, and you know what happens with the chlorine radical, right? Okay, you continue to go through the cycle 1 as we have seen just now. For the ClO2 dot here, now because of the close proximity of the oxygen atom here, so you have this homolytic fission along this ClO bond to reform the oxygen molecule and the Cl radical. So overall reaction is still the breaking down of ozone, 2 molecules of O3 into 3 molecules of O2 gases. So you see that, right, this is another mechanism you can propose to cause the destruction of O3 into O2. Now for the third proposal, mechanism is right. So now we're introducing bromine. So we have bromine. Bromine is a even more stable radical than chlorine because it's less electronegative. It doesn't require more electrons compared to chlorine based on the electronegativity. So if you have these two species here, the bromine oxide and chlorine oxide radical, so they form, right? But the thing is, when they combine, they just split straight away into the oxygen molecule, and because on their own, they can be stable. So you have either this top part, or when you have the halogen radicals, they quickly form a bond. Okay, because when you have this heteronuclear diatomic halogen, it is actually stable. Okay, stable compared to its separate radical. But the thing is, again, in the presence of ultraviolet rays here, the homolytic fission causes it to split, right, to form its individual radical, and then on their own, it breaks down the ozone like we have seen in cycle 1 and cycle 2, and the net effect is still the same when you have 2O3 to 3O2. Okay, so I hope that with this part, you understand what are some of the possible mechanisms of the breaking down of the ozone layer into oxygen gas. So we'll see you next time with Antarctic ozone hole. Cheers.